This tale of two cities of a desert morning. Atomic age is born. A scientific thunderbolt gives a preview of its destructive force. From the instant of that first blast until Hiroshima vanished from the list of living cities, closely guarded plants in New Mexico, Tennessee, and the state of Washington continued their work to shorten the war.
In this video, we're going to talk about nuclear fission. Unstable radioactive nuclei, which occur naturally, sometimes emit strong radiations, especially in isotopes of uranium like uranium-238 or uranium-235. The disintegration converts the uranium isotope into stable lead, and in the process emits energy in the range of 1 to 5 mega-electron volts. That's 1 to 5 million electron volts, and even higher amounts of energy can be released by breaking unstable nuclei into even more parts. In 1939, a German scientist named Otto Hahn discovered that breaking up the nucleus of uranium-235 into two parts emits 200 million times the energy of the neutron which triggered it. He, along with his two colleagues, Lisa Meitner and Fritz Strassmann, found that when the nucleus of uranium-235 is bombarded with neutrons, it will absorb one of the neutrons. This results in an unstable compound nucleus, and the nucleus breaks into two equal parts. This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into two equal masses, releasing enormous amounts of energy, is called nuclear fission. In the process, uranium-235 initially absorbs a slow-moving neutron, thus forming a highly unstable compound nucleus, uranium-236. This is what triggers the nuclear reaction. During the process of fission, uranium-236 splits into two product nuclei, which are barium-141 and krypton-92. You should notice that a barium atom has 56 protons and a krypton atom has 36 protons, which add up to the uranium atom's 92 protons. The unstable uranium-236 nucleus also releases 3 neutrons in the process. This happens because barium-141 has 141 neutrons, and krypton-92 has 92 neutrons, adding up to a total of 233 neutrons. To balance the equation, uranium-236 must emit 3 more neutrons. The chemical equation of the nuclear fission reaction taking place can be represented by this equation. So as you can see from the equation, one neutron combines with uranium-235, forming an unstable compound nucleus, uranium-236. This unstable nucleus splits into two stable nuclei, barium-141 and krypton-92. In addition to these two nuclei, 3 neutrons are also emitted, as well as a high amount of energy, denoted in the equation by Q. Since uranium-236 emits 3 neutrons in the reaction, these neutrons can be absorbed by other uranium-235 nuclei, resulting in a chain reaction. This leads to exponentially high amounts of energy being released by a single reaction. So, in this video, we've covered that nuclear fission reactions result in massive amounts of energy being released. Now, these nuclear reactions are most well known for the part they play in nuclear bombs, but they are also an essential part of nuclear reactors, which have the capability to provide mass amounts of energy with relatively low cost, but that's a different topic altogether.
The film opens with quick shots of Erwin Schrödinger and Niels Bohr. A Gillespie car of the University of Brussels follows, and then the camera refocuses on Schrödinger and Bohr. Erwin Schrödinger and Niels Bohr, followed by Picard. Schrödinger, who developed wave mechanics, never agreed with Bohr in quantum mechanics, nor with Werner Heisenberg's uncertainty principle. Solvay gave Heisenberg an opportunity to discuss his new theory. Here's French physicist Léon Brillouin, Hendrik Kramers, Bohr's former assistant, and Paul Dirac talking with Max Born, whose statistical interpretation of the wave function ended determinism in the atomic world. These men, Bohr, Heisenberg, Kramers, Dirac, and Born, together with Wolfgang Pauli, represent the founding fathers of quantum mechanics. On the other hand is Louis de Broglie, who wrote his dissertation on the wave nature of matter, which Schrödinger used as the basis for wave mechanics. The owner of the camera, Irving Langmuir, is seen chatting briefly with Bohr. At Solvay, Bohr refined his thoughts on complementarity and sparred with Einstein over the implications. Here he's with Paul Ehrenfest. Kramers' work in Copenhagen on dispersion theory was essential to the development of quantum mechanics. Langmuir, an American chemist at the GE lab in Schenectady, hence the camera, had recently broken his leg and appears to explain to Ehrenfest how he gets around. By 1927, Dirac in the middle had independently developed quantum mechanics and made other significant contributions, as had Wolfgang Pauli, who formulated the exclusion principle. A lively Madame Curie, Born and Pauli working out a problem. Note the changed demeanor as the participants exit from the meeting, except for the smiling William Lawrence Bragg and Peter Debye, Arthur Holly Compton, Owen Richardson, Max Born, Madame Curie, Hendrik Kramers, H.A. Lawrence, Paul Langevin, Albert Einstein, whose famous response to Born and the statistical interpretation of the wave function was, "God does not play dice." Bohr, Planck, Pauli, and Belgian soldiers, a portentous conclusion.
Competition. Well, I have to say it may be daunting for Ian. It's very daunting for me because I've come here to the Science Museum, so I'm absolutely not a scientist. And I have great difficulty understanding even the most fundamental scientific ideas. It's true that it was reading Thomas Power's book, Heisenberg's War, that first set me thinking about the play. It was because I'd never... I have to say, my background is in philosophy, so I knew something about what Bohr and Heisenberg had been doing in the 1920s, because the implications of quantum mechanics are philosophically so strange, and they don't get any less strange. They become stranger over the years. But I'd never heard about Heisenberg's trip to Copenhagen in 1941 to see Niels Bohr. I never heard about the disputes that it had aroused. And when I read Thomas Power's book, I thought the combination of that and the parallel with Heisenberg's uncertainty principle suggested a way of coming at a topic that's always interested me, which is the difficulty of ever knowing why people do what they do, even of knowing why one does what one does oneself. And I suspect that it is like the behavior of physical objects, particularly of particles, in Heisenberg's principle. It is theoretically impossible. There is a theoretical barrier to ever knowing everything about human thought. It's not just the matter of knowing more about the way the brain functions. There is a theoretical barrier to ever having the whole truth about things. So that was what set me off. Powers' thesis in the book, it's a very generous book. He's a science journalist, and he writes with great clarity and force. and he is one of Heisenberg's very few thoroughgoing defenders. And he has a double thesis in the book. The point being that the Germans did a lot of research into apparently trying to build an atomic bomb and got absolutely nowhere near it at all. Why not? And Powers' thesis is partly that there was a lack of zeal, a lack of interest among German scientists in doing it. They were keen not to pursue this goal too hard. And as well, he has a second part of the thesis that Heisenberg did in fact know much more than he revealed. He had actually done the crucial diffusion equation, and he cooked up, this is Thomas Powers' phrase, a fictitious version to conceal his real knowledge. Well, Powers has been much attacked by other people for his book, and I have to say I don't accept his view that Heisenberg had actually done the equation and concealed it. I don't think that's plausible. But I do think there was a lack of zeal. But then so does everyone, even people who are very sharp critics of Heisenberg agree that on the German side there was a lack of zeal. And on the Allied side, it was a formidably difficult task. It was an incredibly difficult task. And it required a great deal of zeal and an enormous amount of effort and determination and commitment by everyone involved. Otherwise, we would have never have got there ourselves, for better or for worse. So that's my involvement in the book.
I'll come back later to the questions more about the